Alright, welcome to another one of Darren Grasso's lectures. Just kidding. It's still exploring quantum optics with me. Oh, my name's Paris, by the way. I don't think I said that. My name's Paris. Nice to meet you. Probably by this time we've already because this is the second video, we probably already met via Zoom. So I'm introducing myself for a second time. I also deeply regret ending my last video with cheers, so I apologize for that with as much sincerity as is possible. Let's go through some of the theory and some of the stuff you may not really understand yet. It's totally possible that you're like, what's polarization of light again? That's okay. Don't worry about it. We're gonna cover some of that. So I guess I want you to have a look at this a little. So this is your manual. So turn to this page. It probably helps to have it open. One thing is that we're not there yet. Okay, never mind. There's a few typos in this manual, so be aware of that. Hopefully by the time you get it, I would have gone home and fixed them all up, because the first group that have gone through this lab have picked up a lot of them. So hopefully they'll be corrected, but they might not be. The first one's here. This is just totally wrong. I'll just show you what's right when we get there. So the idea is, we've got an electric field. Let me attempt to draw something in 3 dimensions. This is probably going to end badly. So some Cartesian, and it's coming this way, up from the corner. Can you see that? I think you can. Part of my screen is covered with the glove, so I can't even see what's happening. I think it's fine. Hopefully my voice is not too loud. I'm right next to the microphone. So say it's, kind of coming in. That is not what I wanted to happen. So that's coming in like that. It's not coming just across. It kind of looks like it is, but it wasn't meant to. It looks like it's just in the XY plane. In the YZ plane, I mean. Okay? But it's meant to be coming through all three, so it's moving along this axis there. Okay? So generally when we talk about light, we don't talk about electric and magnetic fields. We don't talk about both, we just talk about one because it defines the other one. So we just say this is the electric field. So that's the polarization of the electric field. Okay? It's it has some, it's the direction that the electric field oscillates. That's what we call the polarization. Okay? So it's it's in that direction. That's E, or otherwise equivalent to that direction. We could say both, because this one implies it's here and it goes like this, and this one implies it's there and it goes like this. So those are two they're just a phase shift. So if I look at the phase of this one, I just have some arbitrary reference. I'll say it starts up here, and the electric field E, the magnitude in that direction, goes like that. Okay? Whereas this one, I take that same reference point, and this one's instead starting here. Okay, but they're parallel. They're oscillating in the same plane. Zip, 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 zip. Just that. There's a phase difference. So these are the same. If I was looking at the wave coming towards me, then I'd have some axes, and these will be a different set of axes. So say these are I don't want to use X, Y, Z because I've defined them. So these are the, come on guys, help me out. These are the P and Q axis, okay? And I've aligned the P axis to be such that it comes out on one side of the wave and the Q axis comes out on the other side. So then my wave seems to be oscillating like that. So it's going like that. Whoop. Okay, and I could have equally drawn that like this. That's what I'm trying to say. So I'm watching the wave come towards me, and it's linearly polarized, so it's oscillating like that. Okay? That's sort of the idea. That's what we're going to be talking about a lot. It's just which direction is the polarization, which direction is the electric field oscillating. We're not going to worry about the magnetic field. The magnetic field is just going to be like perpendicular to that. I think it's actually on this side. But again, they're the same, just with the phase shift. So I could write it there, but with another phase shift. Okay. What else do I talk about? So I talk about the frequency. Hopefully that makes sense. This thing is oscillating over time. So it's propagating and oscillating. And we usually... Oh, do I want to talk about that yet? Yeah. So we'll just say it's a cosine. So E equals E naught. Is that the... So I'm using EX and EY. What I really should be doing is A. So say we've got some electric field. Forget all this. We're talking about a different system now. So I'm going to use X and Y again. So we've got an X and a Y. And we're saying that this is E, right? So it's got an X component and that's it. So we could write that as E vector equals A. And it's got a length, this vector, A naught. So that's an A naught cos kz minus omega t. Okay, so this is the z-axis. The wave is coming towards us like that. All right, out of the page. Yep, so this term, this is all just a phase term. All right, so you've got a wave number here, which is proportional to the frequency. This is essentially saying, because we want to just know what the amplitude is at a certain z and at a certain time, right? We just want to plug that in and know what the phase of the wave is, okay? So this just takes into account the phase due to how far it's traveled. So like moving from there to there, based on the frequency, how much has that phase changed? You know, it's like K equals omega on C, so we know that it's moving at speed C, and then how many oscillations have occurred as it's moved, right? So this is the amount of cycles, how many full periods has it moved. So it's got units of hertz per meters per second. So it's got units of per meter. So it's like radians per meter, and then you times that by Z, and you're just getting radians out. Okay, so it's just like in moving from there, propagating from here to here, this point, how much phase did we just cover? Oh, well, we covered whatever this number is, say it's 10, or say it's 2 pi radians per over 1 meter. We times it by 1, we get 2 pi radians over that distance, which means it went 1 period's worth across those two. But in that time, you know, however many seconds that took, it also oscillated. And so our net phase difference is whatever that minus whatever it usually oscillates over time, and it just gives you the net phase at any position and at any time. That may be kind of like a little bit vague, but you can go through it and think about it a bit more. But that's the idea. It just gives us whatever the phase is, and therefore whatever the amplitude is at any point. Okay. So that's an electric field. You know, it oscillates in a particular direction, and we call that direction the polarization. Well, that direction is aligned with the polarization vector. Okay. So there's a bunch of questions here that kind of get you to think a bit more about that. I think one thing that will be illustrative is, so the other thing is that we'll usually write that as e to the I, kz minus omega t, and we'll just take the real part of that. Okay, and that tells us what the actual amplitude is. We just use the complex notation because it's convenient. For example, if I want to add a phase shift, I can just times by e to the I phi. I can't really do anything like that with a cosine. But if I times by this, then I get e to the I kz minus omega t. plus phi. Great, you know, it's phase shifted. Okay, that's it. So one thing I think that'll be illustrative. So let's say I have something polarized in the XY at 45 degrees. Okay, so clearly that means it's going up and down, right? So how would we write that? Say it has a value A, AX, AY. Sorry if this notation is different to what's in the book, but this is different from what's in the manual, but this is what I'm gonna change it to. This is what I should have done in the first place. So how would we write that? Well, we know that, so this is still E, we're calling it E vector. So we're saying that E is AX cosine KZ minus omega T. Well, let's do the EI KZ minus omega T plus AY EI KZ minus omega T. Okay? So I take the real part of that, real zip, and I'm just left with the cosines. Okay, so let's say for this to be 45 degrees, since 45 degrees, AX has to equal AY, right? So then what I'm getting is E equals, let's just call this A, then it's A, sorry, and this should have an X. That's the X direction, that's the Y direction. I'm just adding unit vectors down. You can't see, there you go, that's a bit better. Okay, so I just put in the unit vectors. So this is on the X direction, this is on the Y direction, but they're both the same. KZ minus omega T, X plus cosine. I could have just written that once too. I should have done that. Anyway. Right, so they're both cosines. So whenever this one is increasing, so is this one. Whenever this one's decreasing, so is this one. They're in phase, right? They're perfectly in phase. So I've got an X direction oscillation like that. Like this. And I've got a Y direction oscillation like this, but they're perfectly in phase. So the Y component, the X component is increasing, so is the Y component, so it goes like the net amplitude is this way, right? I just sum the components, bam, and then they're both coming back this way. Now the net electric field amplitude is that way. So overall it's going okay, I hope that makes sense. Now, what can happen is, I can say, new page. Oops, okay. Long video number 2. Okay, what did I want to say? Yeah, so now let's say I had AX equals AY equals A. So I'm assuming that the components are the same amplitude. They don't have to be. You can imagine back here in the last page, hopefully you've still got that in your mind, or you can rewind. If one amplitude was bigger than the other, say the Y amplitude was bigger than the X, then you're like kind of skewed towards this way. So it's going like a big Y and a small X. They're still in, if they're still in perfect phase, you've got this. Okay? And the net thing is to kind of be not 45, but a bit closer to the Y-axis, and then you're oscillating like that, and like that, and like that, and like that, sort of closer to the vertical, okay? Because the components are unequal. It's more skewed towards the Y direction. Okay, the other thing you can do is have equal components, and you can also have unequal components and do this. but you can add a phase shift. Okay, so you can do a phase shift with equal components. This is one of the questions in there, so I'm kind of walking you through it. I think it's new and I'm not there, so it's hard, but you can also ask me questions on Zoom, so don't freak out. So say I've got the x component, A, cosine omega t, or we can do E, just remember that we're going to take the real component, so it's just going to become cosine. So this one we just do as the same as before, x, and then the y plus A, E, I, K, Z minus omega t, plus, let's make it a 90-degree shift, alright, which is the same as me writing I, K, Z minus omega t times e to the I phi. Phi is pi on 2, alright? So we can do that. And then we can take the real and imaginary components. And remember that e to the I phi equals I, okay? So, and e to the I kz minus omega t equals equals cosine of all that plus I sine of all that. So if you times that by I, then this becomes imaginary. So I times that equals I times that plus I squared times that. And I get a negative sign here and a cosine. Okay, so if we're looking at this one, hey Tim, I'm filming. So back to our example, you can see, good. Comparing these two, we've got a pi on 2 phase shift. So the x component, EX, would start up here. Right, that's this oscillation. This is it, like that. Alright, and then the y, EY, is the same, but it's kind of shifted by pi on 2, which is where cosine is 0, so we're here. So plus pi on 2, I'm going to shift it this way. Yep, so you're going to get something like this. Alright, so then that's your y oscillation. I'm not sure if I got that 100% right, but you can check. So then, what happens to our polarization vector over time? Okay, so that's one of the questions. So answer that, and then I'll make the next video. Thanks for watching.